Welcome to today's paper reading. Today's paper is titled, From Fake to Real, Pretraining Unbalanced Synthetic Images to Prevent Spurious Correlations in Image Recognition. This paper was published on AR14 by Maan, Qraitem, and colleagues from Boston University. The abstract highlights a significant issue in visual recognition models, where they tend to learn spurious correlations due to biased training sets. Specifically, certain conditions, such as indoors, are overrepresented in specific classes, like big dogs. Synthetic data offers a potential solution by augmenting underrepresented subgroups in the real dataset. However, mixing real and synthetic data introduces new biases due to distributional differences. Prior approaches have not effectively addressed this, leading models to learn biases based on whether data is real or synthetic. To tackle this, the authors propose a two-step training pipeline called From Fake to Real, FFR. This method first pre-trains unbalanced synthetic data to learn robust representations, then fine-tunes on real data, avoiding exposure to the statistical differences between real and synthetic data. This approach improves worst group accuracy by up to 20% across 3 datasets. Visual recognition models often learn spurious correlations due to imbalances in the training data. For instance, a model might incorrectly use gender as a predictor for smiling. To address this, synthetic data has been used to mitigate bias. Prior methods like additive synthetic balancing, ASB, and uniform synthetic balancing, USB, have been introduced, but they can still lead to bias due to differences between real and synthetic data. Our proposed solution, the From Fake to Real, FFR, pipeline, uses a two-stage training approach to effectively mitigate this bias by separating synthetic and real data training. Figure 1 illustrates the comparison of rise saliency maps for a model trained to predict the attribute smiling, given a bias toward gender B where most women are not smiling. The figure shows 2 scenarios: A. Prior work in synthetic augmentation, which does not address the unexpected bias toward the pair, gender B, data source G, leading to the use of spurious features and an incorrect prediction of not smiling, and B. Our approach, From Fake to Real, FFR, where the synthetic and real data are separated into 2 training stages, thereby mitigating the bias suffered by prior work and enabling the model to learn the correct features, mouth, and correctly predict smiling. In the realm of bias mitigation, synthetic data methods like USB and ASB have been employed to balance underrepresented subgroups and augment biased datasets. However, these methods introduce bias toward the distinction between real and synthetic data. On the other hand, synthetic data-free methods modify architecture or training procedures to mitigate bias without relying on synthetic data. These include group DRO, which adapts model optimization based on the worst-performing group, and methods that operate without bias labels. Additionally, our work addresses spurious correlations, where underrepresented groups in training lead to incorrect class correlations. Synthetic data is shown to be effective in mitigating these spurious correlations. Visual classification models often rely on spurious correlations in the training data that do not reflect real-world distributions. This bias occurs because the training set encodes correlations between classes and biases, leading models to make incorrect predictions based on these biases. To address this, synthetic data from generative models is explored to augment real datasets. However, the distribution of synthetic data differs from real data, making it challenging to balance biases. The From Fake to Real, FFR, pipeline is introduced as a solution, which involves a 2-stage training process: pre-training on balanced synthetic data and fine-tuning on real data, thereby mitigating bias. Figure 2 provides an overview of the From Fake to Real, FFR, training pipeline designed to mitigate bias by incorporating synthetic data. In the first stage, the model is pre-trained on a balanced synthetic dataset, enabling it to learn robust representations across different subgroups. This step is crucial as it ensures that the model does not develop biases towards any particular subgroup. In the second stage, the model is fine-tuned on real data using either empirical risk minimization, ERM, or other common synthetic data-free bias mitigation methods. By separating the training on real and synthetic data into distinct stages, FFR effectively prevents the model from being exposed to the statistical differences between these two data sources. This approach helps to avoid the issue of bias that typically arises when models are trained on mixed real and synthetic data. For a more detailed discussion, refer to section 3.2 of the paper. In this section, we will discuss the datasets used in our experiments, the metrics employed to evaluate model performance, and the methods applied. We used three standard bias mitigation datasets: CelebAHQ, Spurious animals, and UTK-face. These datasets were chosen to study the effect of synthetic augmentation on varying amounts of bias. We fixed the bias and target attributes per dataset and manually varied the bias according to 5 main ratios ranging from moderate to severe. To measure the model's spurious behavior, we used worst accuracy, WA, and balanced accuracy, BA. We also implemented several methods to incorporate synthetic data, including USB, ASB, and our proposed method FFR. These methods were combined with empirical risk minimization, ERM, and other bias mitigation techniques such as group DRO, resampling, and deep feature reweighting, DFAR. Figure 3 illustrates the comparative performance of our synthetic data augmentation method, FFR, against prior work methods, USB and ASB, across 3 datasets and various bias ratios. The figure highlights that FFR either matches or enhances the worst and balanced accuracy of ASB and USB across each dataset and bias ratio. Notably, FFR demonstrates improvements over USB and ASB on UTK-face and a bias ratio of 95% by over 10%. This enhancement is attributed to FFR's ability to address the bias between real and synthetic data, enabling more effective bias mitigation. Additionally, the figure shows that while prior work augmentation methods maintain stable performance on Spurious animals across bias ratios, their performance significantly decreases as bias increases on CelebAHQ and UTK-face. In contrast, FFR maintains stable performance, indicating its robustness to more severe bias. Figure 4 illustrates the comparative performance of synthetic data-free bias mitigation methods, including group DRO, resampling, and deep feature reweighting, DFAR, against methods that use synthetic data augmentation such as USB, ASB, and our proposed FFR method. The performance metrics are averaged across 3 datasets and 5 bias ratios. Notably, FFR demonstrates superior performance in enhancing the effectiveness of non-synthetic data augmentation methods. This figure highlights that while synthetic data-free methods significantly improve the performance of synthetic data augmentation methods, FFR remains the most effective standalone method. Additionally, combining FFR with synthetic data-free methods further enhances the performance of group DRO and resampling. For a detailed discussion, refer to section 4.2. Figure 5 illustrates the Tiacini projections of real versus synthetic data using different synthetic augmentation methods, USB, ASB, and FFR. The figure clearly shows that FFR is the most effective method for projecting real and synthetic data closely together. This outcome is attributed to FFR's reduced sensitivity to the bias between real and synthetic data, enabling it to learn more effectively from both data sources. The distinct clustering observed in USB and ASB methods indicates their reliance on features unique to each data type, such as synthetic artifacts, which contrasts with FFR's use of core, unbiased features. This analysis further supports the claim that FFR is superior in mitigating the bias arising from the distributional differences between real and synthetic data. Figure 6 presents saliency maps generated using RISE for predicting big dogs and small dogs, comparing methods ERM, ASB, USB, and FFR. The real images are sourced from Spurious animals, while the synthetic data is from Stable Diffusion version 1.4. Notably, FFR is the only method that accurately localizes the relevant dog features without being influenced by spurious background elements. This demonstrates FFR's superior ability to focus on core features, enhancing its predictive accuracy. Refer to section 4.5 for a detailed discussion on the implications of these findings. Table 1 presents the ablation study results of the FFR stages on the Spurious animals dataset, averaged over all bias ratios. The table clearly shows that the inclusion of both stages in the order stage 1 followed by stage 2, 1-2, achieves the best performance, with an average WA of 72.6 plus or minus 2.3 and BA of 83.4 plus or minus 0.3. This result underscores the importance of the method's design, where pre-training on balanced synthetic data, stage 1, is crucial before fine-tuning on real data, stage 2. The table also highlights that stage 2 alone yields poor performance, as it trains the model with ERM on biased data without the benefit of pre-training, thus learning the bias. Conversely, stage 1 alone improves performance but does not reach the optimal results achieved by the combined stages. This analysis confirms the effectiveness of the FFR method design and its ability to mitigate bias in the dataset. Table 2 presents an ablation study on the pre-training distribution used with the FFR method over the Celeb AHQ dataset, averaged across all bias ratios. The table highlights the critical importance of using a balanced distribution during pre-training to achieve optimal performance. Specifically, it shows that employing a balanced pre-training distribution results in a significant improvement in worst accuracy, WA, compared to using a biased pre-training distribution. The results underscore that FFR with balanced pre-training achieves the highest WA of 82.3 plus or minus 1.1, while biased pre-training leads to a substantial drop in performance. These findings reinforce the necessity of a balanced synthetic distribution during pre-training to effectively mitigate bias and enhance model performance. Table 3 presents a comparison of the performance of uniform synthetic balancing, USB, additive synthetic balancing, ASB, and our method from fake to real, FFR, on both synthetic and real data using the Spurious animals dataset. The results are averaged over all bias ratios. Notably, FFR demonstrates superior performance with a worst group accuracy, WA, of 72.6 plus or minus 2.3 and balanced accuracy, BA, of 83.4 plus or minus 0.3, significantly outperforming USB and ASB. This indicates that FFR effectively mitigates biases between real and synthetic data, leading to more accurate and balanced predictions. For further discussion, refer to section 4.4. The From Fake to Real, FFR, framework effectively addresses the bias issue by separating the training process for synthetic and real data. This approach has shown to enhance the worst group accuracy by up to 20% compared to previous methods. Additionally, FFR maintains its superior performance even when combined with synthetic data-free methods. However, the use of large pre-trained text-to-image models for generating synthetic data introduces certain limitations. These models can inadvertently inject biases into the generated data, and the ability to generate a balanced dataset can be compromised by imbalances in the pre-training distribution. Future research should focus on developing more accurate and fair generative models to mitigate these issues and improve the overall performance of FFR. Thank you for watching.